Welcome to Chemistry 111. We're going to continue with Chapter 3. At this point, we are looking at the math of Chapter 3. We focused very heavily on how do we name stuff, but now we need to also focus on how do we deal with these on the macroscopic level. How do we deal with molecules that when a typical molecule is too small to weigh? Even if you took something like, I don't know, like even a simple protein is still very difficult to weigh. Proteins are incredibly big, incredibly heavy on an atomic level, but still even those are really hard to weigh. So that's where we introduce the idea of the mole. Quick reminder, mole is a number, a magic number that is 6.022 times 10 to the 23rd of an object. So whenever I say a mole of this, I'm saying 6.022 times 10 to the 23rd of that. If I say half a mole, I'd be half of that number. So it'd be like 3.011. If I said 2 moles, I'd be doubling that number. Just like you'd say 2 dozen, half a dozen, 3 dozen, you could work the same way. This number is also an important part of the school year, and that, at least for chemistry, we are one chemistry, math has pi day, well, chemistry has mole day. It's 1023 every year. 1023, that's our 10 to the 23rd. We usually celebrate that week by doing a bunch of chemistry demos and make a big presence on campus. But so mole is our big magic number that we'll be using. Yeah. Let's see. Okay. So we'll start off whenever we do a conversion like this by saying a fraction over 1. And then we're going to either multiply by Avogadro's number or divide by Avogadro's number to cancel out our starting unit. So if I have 5 moles of CO2 and I want to know how many molecules of CO2 you have. So I'm going to start off 5 moles over 1. Then I'm going to say, okay, if 1 mole equals 6.02 times 10 to the 23rd, I need, because I have mole on top of this fraction, I'm going to need mole on bottom of that fraction. And so 1 mole equals 6.022. So I'm going to multiply 5 by 6. And because it's times 10 to the 23rd, I need to move the decimal place over because 5 times 6 is 30. However, remember, in scientific notation, we want the number between 1 and 10, not above 10. So 30, we have to move it to 3 and move the decimal place 1 over to make it, instead of 10 to the 23rd, 10 to the 24th. Now, if I'm to punch this into my calculator to do the math, I'm doing 5 times 6.02 times 10 caret 23. Or alternatively, I could have said 5 times 6.022 E23, because that E stands for the times 10 to the whatever power follows that E. So that's how I would punch that into my calculator. Now, if I want to say turn atoms into moles, if I have 3.1, yeah, try that on your calculator though, but if I have 3.18 times 10 to the 25th atoms, and I say how many moles is that? So 1 mole goes on top, and the Avogadro's number of atoms goes on bottom. So I'm going to divide by 6.022 times 10 to the 23rd. Dividing by that, I get 52.8 moles. Please, please, please actually try this one on your calculator, because this is one where multiple exponents. So it's very easy to type this into your calculator wrong. If you type this into your calculator wrong, you will get a completely different number that's way too big or way too small. So also note, in the first example, I used a mole of molecules. This time I'm using a mole of atoms. So mole could work with anything, but typing this into your calculator, it would look like this. 3.18 times 10 to the 25th divided by 6.022 divided by 10 to the 23rd. Alternatively, you could do it 3.18 E25 divided by 6022 E23. The one thing you got to make sure, just because there's a multiplication, just because right here doesn't mean you type it in as a multiplication right there. The only way you can type that in as a multiplication is if you have a parentheses around the 6 and the 23. You have a parentheses over that whole thing. Otherwise, what you would be saying, 3.18 on top times 10 to the 25th on top divided by 6 on the bottom times 10 to the 23rd on top. Because order of operation says just multiplication, division, multiplication in that order, not multiplication, multiplication, then division. So you need to either make sure you type it in like this, or you type it in order of operation, or you include parentheses. So I want to avoid you making silly mistakes, because it's all well and good if you can set this up and make it look pretty on paper. It's another thing if you know how to use your calculator to avoid these dangerous pitfalls. Just want to make sure. Yeah. Okay. Now, another thing we're going to focus on is molar mass. When we started off measuring atoms, we had an atomic mass, and they were weighed by atomic mass unit. It just so happens that the conversion of grams to AMU is 1 gram is 6.022 times 10 to the 23rd AMU. Such that we've defined AMU, so the weight of 1 carbon atom weighs 12 AMU. Thus, 1 mole of carbon conveniently weighs 12 grams. So 1 atom of carbon weighs 12 AMU, 1 mole of carbon weighs 12 grams. Now, if you look at the bottom of the periodic table, you look at the bottom of each element on the periodic table, you will see the atomic mass, the weighted atomic mass. However, using this quick conversion, it can also be converted into from atomic mass or molecular weight into molar mass. That instead of being AMU per molecule, it's also grams per mole. So the same number for carbon could be instantly scaled up without doing any real mathematical division. The weight on the bottom is the same. So if I'm looking at 1 atom of carbon, the average weight of an atom of carbon is 12.01 AMU per atom. If you're looking at the average weight of a mole of carbon, it'd be 12.01 grams in that mole. So I can use the exact same number. We don't have to convert it. That's the convenience of the AMU to gram conversion. That's the convenience of the idea of a mole. We can use those numbers. So we will calculate, if you are asked to calculate the molar mass of any given compound, how do we do that? The molar mass of a compound is found by summing up the individual molar masses of each element and taking into account their quantity. So carbon monoxide, you're going to have to add the 12 grams from carbon and the 16 grams from oxygen. So the weight of carbon monoxide would be 28. If I'm looking at carbon dioxide, CO2, you'll have the 12 grams from carbon, but now you would have 2 oxygens. So 16 times 2. 16 times 2 is 32. So 32 plus 12 is 44. So the molar mass of carbon dioxide is 44 grams in a mole. These will allow us to calculate the amount of atoms present in a given mass and convert a quantity of moles to its respective weight pretty easily. So all you have to do is be able to find the element on the periodic table and add up all the individual elements one by one by one. Shouldn't be hard, but we got to be able to do it. Okay. Now, here's a shortcut. Now, we've seen that moles is a convenient way of measuring atoms. So, in moles, we can calculate the mass of a compound. Almost every problem in this chapter is going to go through moles one way or another. So, if we start with mass, we're probably going to have to go to moles. If we start with atoms, we're probably going to have to go to moles. So, knowing these conversions will help us. If I'm going to moles to molar to grams, I'm going to multiply by my molar mass. If I'm going from moles to atom, I'm going to multiply by my Avogadro's number. The generalized equation is here's a weird thing. The abbreviation for moles is going to be the small letter n. I don't know why. Don't ask me for this one, but whenever we say small letter n, that's going to be our moles. In some equations in the future, you're going to see the small letter n, that's usually moles. But moles times Avogadro's number would give us either atoms or molecules. Because moles times atoms over moles cancels out the moles. N times molar mass is going to give us just the mass, because moles times grams over moles, the moles cancel out, we're left with grams. So how do we go back? How do we go back to moles? Mass divided by molar mass. How do we go back from atoms to moles? Atoms divided by Avogadro's number. We're going to need to be able to convert between the two without getting lost. So, using Avogadro's number and molar mass, we can easily convert between one and the other. So here's some practice problems here. And then I'm going to actually start doing some. But hypothetically, we have 3 moles of CO2. How much would it weigh and how many molecules would it contain? Don't forget, we've already done this. The molar mass of carbon plus 2 times the molar mass of oxygen. So I'm actually rounding from what we have on the table, but usually it's going to be a small enough number that it's not going to affect it by much. Especially considering I have 3 sig figs. So the number I have 2 sig figs here in my starting number. So 12.01 is going to be a rounding error. So 12 plus 32 is 44. Setting this up, 3.0 moles times 44 grams per mole gives you 132 grams. Hypothetically, if I was rounding to the sig figs, I'd say about 130 grams. Because 2 sig figs in my starting number, I should probably only get 2 sig figs in my ending number. Doing the other way. Moles to atoms, setting up moles on top, moles on bottom. So 3 times 6.02 times 10 to the 23rd gives us 1.8, 10 to the 24th. So working my way one by one by one, what is the answer to this question? We have 36 grams of water. How many molecules of water are there? Okay. Our question was, if I have 36 grams of water, how many molecules of water do we have? Water is H2O. Let me check. Yeah, okay, H2O. So, with that in mind, First, we have to go to moles. We have to look up what is the molar mass of water. The molar mass of oxygen, as I said, is 16. The molar mass of one hydrogen is approximately 1. So because there's 2 hydrogens, 1 times 2, 2 plus 16, we have 18 grams per mole. Now, because I have grams on top, I need grams on bottom. So I'm going to set this up as 18 grams of water in 1 mole of water. So that grams cancels grams. And the result would give us the number of moles. Now, I could answer this question and then move on to the next part, but I can set it up as one big equation as well. But 36 divided by 18 is 2. Now the next one, Avogadro's number is atoms per mole. So in 1 mole of water, I have 6.022 times 10 to the 23rd atoms. Setting that up, so moles cancel moles. Actually, not atoms, molecules in this case. So working my way all the way through, 36 divided by 18 is 2. 2 times 6.022 puts us at 1.2. Let's see. Yeah, essentially 1.2 times 10 to the 24th molecules. So I broke down a complicated problem into essentially, I'm just converting one to the other to the next. I'm setting this up so each conversion cancels the last. And that's the process by which you'll do a lot of the math in chemistry. You need to convert one thing to another, always canceling out the last. Sorry, I need. Oh. So if you didn't catch that on the doc cam, there it is again. That's how we will always do all the chemistry. At least I will try to show almost all conversions done in that way. This is through dimensional analysis. So practice. First, what is the molar mass of iron? Oxide. Then what is the molecular weight of potassium permanganate? And then how many molecules would be in 1/4 moles of potassium permanganate? So answer those all, just practicing what we got. Pulling up that. So iron. Some of this stuff you have to go to the table. There's some people will know the numbers. Some people are that good. Some people will memorize a lot of them. You use it enough and you will. I know most of these, but we'll go. If you look at iron, you can round to 56, but truly iron is something like 55.85 grams per mole per iron. That's for iron. There are 2 irons, so times 2. Now, oxygen, as I said, was about 16 grams per mole, and there are 3. So I'm going to figure that out. 55.85 times 2, 16 times 3. If you're like, wow, I did that fast. Well, don't be too impressed. I've used iron so many times. It's one of those common things. just like you remember a phone number. You use it enough times, you're going to memorize this. At least back in the day when we had to remember phone numbers. But so 5585, you get the total sum is something like 159.7. That is grams per mole. Now the next one, we ask the molecular weight of potassium permanganate. The molecular weight. Well, potassium is about 39.1 AMU of potassium. Manganese is, say, about 54.94 AMU of Mn. And oxygen, once again, is 16 times 4 oxygens this time. AMU of oxygen. So doing this math, just summing them up, 39.1 plus 54.94 plus 16 times 4 is 15804 AMU per molecule. The only big difference is we asked for this in units of molecules. But really, if I calculated a mole of potassium permanganate, it would be 158.04 grams in a mole. So it works either way. And how did I get that? I looked at the periodic table. How did I get that when I'm so far from the periodic table and I don't always remember all of them? Well, I have an app on my phone. But you could easily find them one place or another, online, on the test, whatever. Now, the last thing, I asked you, how many molecules of potassium permanganate are in a quarter of a mole? Here's the beauty of this. I could have asked you how many molecules are in anything if I have a quarter of a mole. I do not need the molar mass. I do not need that number at all. Mole is independent of what we're looking at. I could have asked how many people are in a quarter dozen of a people? How many eggs are in a quarter dozen of eggs? It doesn't matter what we're looking at. That's going to be independent of the size. So 0.25 moles, set up 1 mole is 6.02 times 22 times 10 to the 23rd molecules. So 6.022 times a quarter is 1.5 times 10 to the 23rd molecules. Okay. Go back to the PowerPoint. And what we'll see, 39.7, 58.04, 1.5. All things considered, we need to know how to find a molar mass, and we need to know how to set up atoms to moles or grams to moles. You do that and you'll be in good shape for this chapter. Now one of the last major things is percent composition. Percent composition is similar to percent by mass, which we kind of looked at. But percent composition is now that we know the molar mass of an element, we're looking at how much of this element is present in the generalized formula. So we're going to look at the mass of the element versus the total mass of the compound. Now, because it's a percent, you always multiply by 100. So in iron oxide, we talked about iron is about 56, oxygen is about 16. So 56 divided by the total mass of what? Total mass of 72 puts iron at 77.8% iron. While Fe2O3, which is instead of iron 2, it's iron 3 oxide, iron is decreased to 70%. Because in the first one, it's 1-to-1 ratio of iron to oxygen. In this case, it's no longer 1-to-1. There is slightly more oxygen. Instead of 1-to-1, it's 1-to-1.5. So for every 1 iron, there's 1.5 oxygens. So it weighs a little bit more, so iron makes up a little bit less of a contribution. That 2-to-3 ratio. You can also use this percent composition to calculate the amount of a given element present. So if you know the percent composition, you can calculate the weight that element's going to give you. Now we're going to use this to determine the formula of an unknown compound. This is maybe the maximum amount of math we're going to do in this chapter. Where this is going to come into play, in real life is, say you've discovered a new protein. You isolated some protein from a plant or from some new insect, and you're trying to figure out what that protein is. One of the ways you can determine is by figuring out how much of each element is present. If you can find out the percent mass of each element, you can kind of figure out what this must be made of. That's one of the things you do. You can burn this and you can get the weights of each element, and you find out, oh, this is so many percent nitrogen, or this is so many percent carbon, and you can kind of figure out, well, there has to be these elements in there. Hypothetically, so working out this, 300 grams of mercury teiodide is 300 grams, contains 183 grams of mercury, 183 grams of mercury. What is the percent of mercury? And then also the next one, 50 grams of zinc chloride is 48% zinc. How much zinc is present? So looking at those. Pull up the okay. So if we're looking at percent equals individual, over total times 100. It should be relatively easy to set this up. You just have to realize which category they fit under. A total sample of mercury iodide. The total sample of mercury iodide is 300 grams. How much of that is mercury? Well, I isolated 183.8 of those 300 grams. Times 100 will give me my percent. So the percent mercury would be the weight of the mercury over the total weight. Times 100 puts it at 61.3%. Working the other way around, we're given the percent of zinc, 48%. And we want to know how much zinc do we have if we have a 50-gram sample. So this one we have to work backwards. We have to isolate. But so how do we isolate that? We're going to cross multiply both sides by 50, divide both sides by 100. So you're going to have 48 times 50 divided by 100 is going to leave our grams of zinc by themselves. If you're at a loss how I did that, what I did to do that, come by, see me. This is some math we need to work on. You don't have to shout out right now. It might be a little embarrassing. But we need to be able to do this and isolate our variables. Otherwise, we will have a really tough time. So 48 times 50 divided by 100 says, okay, of those 50 grams, 24 grams would be zinc. 24 grams of zinc. Where is this going to be useful? Say you have iron ore. You're in a smelting plant. You're trying to figure out how much iron I should be able to get out. Well, if you know the percentage of iron that's in that ore, you should know, well, what weight, if I put in 500 tons of iron ore, you should know what weight of iron I should be getting off. If I'm not getting anywhere close to that amount, then that means we're wasting a lot of iron somewhere. We're losing it. So this is kind of what this can be used for. If you know what this is supposed to be, well, this is how much I should get. I can figure out kind of how much I should get based on this idea. Now, where we're going to take this is to figure out an empirical and molecular formula. We can now talk about the composition of substances by mass, the mass percent, moles. We can look at a chemical formula. How do we actually determine the chemical formula? Well, the molecular formula is the thing we've been dealing with all this time. It's the actual number of atoms of each element in a single molecule. So CO2 is just CO2. Glucose is C6H12O6. If I wanted to say xylitol, it'd be C5H10O5. I'm just spitting out sugars right now, so you don't need to write those down. But the idea is it's the actual number of atoms given in a single molecule of a substance. One of the things we will look at is the empirical formula, which is the simplest whole number ratio of each element in a compound. Empirical means directly observable. When we burn things, we're not going to get that, oh, it's clearly 6 carbons, 12 hydrogens, 6 oxygens. We will get only the ratio of each element. We'll get the ratio of each element. The same way as if I look at a crystal of sodium chloride will just give me that for every 1 sodium, there is 1 chlorine. It won't tell me we have a bajillion sodiums and a bajillion chlorines. It'll just say there is a 1-to-1 ratio. So you're always going to find the empirical formula pretty easily. The molecular formula will be the one you have to scale up to. Sometimes it'll be the same. Water is H2O. The simplest whole number ratio is 2-to-1. The actual formula is 2-to-1. But if you look at hydrogen peroxide, which is H2O2, that's 2-to-2, which simplifies to 1-to-1. So if you was reacting H2O2, you would get, we have a molecule of HO. That's not what it actually is, but it's H. You would get a ratio of 1 hydrogen to 1 oxygen. Now, as I said, many covalent ionic solids will not have a molecular formula. Sodium chloride, silicon dioxide, so like glass, carbon in its simplest form of diamond will have a repeating carbon structure. We're just going to say C, even though it's really like C a bajillion, 3C 10 trillion. It's going to go as far as the diamond goes. So we can't really represent them as a molecular formula. But we're going to be looking at these empirical and molecular formulas. So how are we going to determine these empirical formulas? We're going to use our percent by mass. You could start from 3 points, and the ending point will always be if you have a mole of one compound, and you compare it to the mole of a compound, you're going to get a mole ratio. That's the end goal, what we need, a mole ratio. What is the simplest whole number ratio of this atom to this atom? Sometimes there may be a little bit of rounding. Sometimes you'll have to scale it up. A 1 to 1.5 ratio is actually a 2 to 3 ratio. But we're going to find the simplest whole number mole ratio. So what does that mean? We have to convert to moles. So we could start from mass, and then we just have to convert both to molar mass, to moles by molar mass. But we could also start from mass percent. In that case, we're going to go from mass percent to actual mass to moles before we get our mole ratio. So we could start anywhere in those three regions, but we're all going to get to the same ending point of a mole ratio. Now, I'm going to practice this with some of the easier versions first. So looking at this, flipping .chem, if we have a mixture of copper and oxygen, CuNO, and we have 0.853 of Cu and 0.4265 of O. What is the simplest? What is the empirical formula? The other one is iron and chlorine. Right? In this case, we start with mass. Iron is 31.83 grams, and chlorine is 60.62. Okay, now let's go to the .chem here. When we already have moles, don't look gift horse in the mouth. How do you get a mole ratio? We're going to divide the bigger number by the smaller number. So 0.853 copper over 0.4265 oxygen. And for oxygen, it's just going to be the number by itself. 65 divided by 0.4265. Any number divided by itself is going to be 1. 853 divided by 0.4265 would give us 2. And that means for every 1 mole of oxygen, there is 2 moles of copper. So, meaning the empirical formula must be Cu2O. For every 2 moles of copper, there's 1 oxygen. This structure is copper 1 oxide, bringing us back to our naming, copper 1 oxide. I know that because if oxygen is -2, in order for there to be 2 moles of copper to balance it out, copper must be +1. 1 times 2 is 2. 2 minus 2 is 0. So this has to be copper +1. Looking at iron, this one we have to do a little bit harder. We start with 31.83 grams of iron. We need to turn this into moles of iron. So we use 55.85 grams of iron for 1 mole of iron. And I'll have to do the same thing with chlorine. 60.62 grams of chlorine. The molar mass of chlorine is 35.45 grams per 1 mole of chlorine. Once again, chlorine is one of those elements I know by heart. I'm going a bit fast. I don't expect you to be zipping through this nearly as fast. So we'll work through it. So 31.83 divided by 55.85. How many moles of iron do we have? 0.56. Well, we'll say 57. 5700. Well, 570. That's fine. How many moles of chlorine do we have? 60.62 divided by 35.45 gives us 1.71. If I just figured out based on their weight, what ratio, we would have said, oh, this is clearly close to 2 to 1. However, iron weighs much more than chlorine. Iron weighs much more than chlorine. So the actual ratio is closer to, so taking 1.71 divided by 0.57, that's chlorine, 0.57, or that's our iron. For every 1 iron, we have 3 chlorines. Instead of being FeCl2, we actually have FeCl3, because iron weighs like a little over 30% more. Well, yeah, a little over 30% more. Maybe like 40%, 50% more. Something like that. But with that in mind, we can't simply make an assumption. We have to convert grams to moles, moles to mole ratio. Now, we will not do this problem today. Coming on Monday, we will work through this problem, which uses oxygen, carbon, and hydrogen. This one starts from percent yield and goes all the way to mole ratio. And then we'll finally finish up with maybe molecular formula. So we are almost done with this chapter. And then we will start looking at the old tests. So we'll start doing a little bit of review for the upcoming test. And we'll talk about that on Monday. Don't forget, check what homework is due on Monday. Work on it over the weekend. But you guys are doing good. Keep up good work. I will see you then.